welcome to this new web note on vector series. And as a special case, we'll see at the end a nice discussion about Schauder bases in Banach spaces. First of all, let us talk about series in Banach spaces or normal spaces in general. Recall, so let V be a normed vector space. Okay. The completion of V is a vector space. And since it is complete, its completion is a Banach space. So many of the concepts in this web note can be stated in a Banach setting as well as normal setting. It will not make any difference anyway. So recall that conversions of a sequence of vectors in V. So we are saying, okay, say limit of Vn is equal to V as n goes to infinity if and only if limit of the norm of Vn minus V is equal to 0 as n goes to infinity. So we have used this property of convergence of sequence of vectors in V in a normed vector space, and we have also showed that if Vn converges, then for any epsilon there exists n0 such that for any n and m greater than n0 we have the norm of Vn minus Vm less than epsilon, and we call that Cauchy criteria. Cauchy criteria. In other words, if a sequence is convergent in the normed vector space, it is Cauchy. Okay, the problem is the converse. If a sequence is Cauchy, then it converges only if the normed vector space is complete or is a Banach space. Okay? Great. Now we want to define a series. Okay? Series in V. And the idea here is to look at exactly how we did it on the real line, because the real line is a normed vector space, a complete normed vector space is a special case. So whatever we learned on the real line, we can extend it nicely, as much as we can, to normed vector spaces. So for example, so let's Vn be a sequence in V. Okay, define the new sequence let's call them Sn by in V by Sn equal V1 plus V2 plus Vn. So these are, as we knew from the real line, partial sums. Okay, so we know, for example, it's very important that Sn plus 1 is equal to Sn plus Vn plus 1. Great. So we will say that the series, so we will say that the series sigma of Vn is convergent if and only if the sequence of the partial sums Vk, k from 1 to n, is convergent. Okay, its limit is known as the total sum of the series Vn. Notation, okay, for the total sum, notation, okay, of the total sum, sigma from n equal 1 to infinity of Vn is equal to limit of sigma of Vk, k from 1 to n when n goes to infinity. If the series sigma of Vn n greater than 1 is not convergent, we will say sigma of Vn is divergent. If the series sigma of Vn is convergent, then the sequence of partial sums is Cauchy, which means that for every epsilon, for there exists an n0, such that for every n greater than n0, for every h greater than 1, we have the norm of the sigma of the Vk from n to n plus h is less than epsilon. So this is the Cauchy criteria, and if we have a Banach space, then we know that the series is convergent if and only if we have the Cauchy behavior. In particular, if we take h equal 1, okay, in this case we get so it's h greater than 0, okay? So in other words, this is Vn, Vn plus 1, etc., etc., etc. So the first one is we can take h equals 0. Because if we take h equal 1, it means we have always that jump of 1, Vn and Vn plus 1. So if we take h equals 0, then in this case we get the norm of Vn is less than epsilon. In other words, okay, for every epsilon, there exists n 0, such that for every n greater than 0, we have Vn. And this means, okay, in other words, we have limit of the norm of Vn equals 0 as n goes to infinity. So, conclusion, if let V be a normed vector space, okay, if the series Vn is convergent, then limit of Vn is equal to the zero vector when n goes to infinity. So this reminds us of the case of real valued series. Right? If a series is convergent, then the numbers you are adding must go to zero. Here, if you have a series of vectors which converges in V, then the vectors Vn must go to 0. Next, let us see a criteria. In some cases, in some Banach spaces, like LP spaces, what we call lattice Banach spaces, with special structure, then we do have some extension of properties from series on the real line to these cases, to this Banach space. But in general, we do not. In general, the extension of many of the tests that we learned on the real line for series do not extend to normed vector spaces. So one of them is a special case. Okay, special case. Okay, which is some kind of absolute convergence. So we take, let V be a Banach space. Okay, let sigma of Vn be a series. Okay, such that the series of the norm of Vn is convergent in R. So the series of the norms, okay, is convergent. So now, for any n greater than 1 and h greater than 0, we have sigma of vk from n to n plus h on norm by the triangular inequality is less than the norm of vk from n to n plus h. So what's going to happen is, since sigma of the norms of Vn is convergent, then sigma sequence of the partial sums Vk from 1 to n is Cauchy. Okay? And again, because of this inequality, okay, we get, so the sigma of the vk's, the vectors now, partial sum, is also Cauchy. Okay? Since V is Banach, in other words, complete, okay, we conclude that the series Vn is convergent. So we do have, and it's not very hard, it's very easy by using the continuity of the norm. It's easy to see that the norm of the total sum of the Vn's from 1 to infinity is less than the sum of the norm of the Vn from 1 to infinity. Okay? So this, of course, we should be very careful, because whatever we find here should also apply to the real line. And we know, for example, example, we know that if we take sigma of minus 1 to the n over n greater than 1, so this one, if you take the absolute value, is divergent. This one is convergent, while the series of the absolute value, sigma of absolute value, equals sigma of 1 over n, is divergent. In other words, here, the norms, the series of the norms may be divergent. It doesn't mean that the series of the vectors is divergent. We have to be very careful about this. Okay? Here we have forgotten norm. So of course this leads to what? To the concept of conditional convergence. Conditional convergence. Okay? So when do we have this? This is if sigma of Vn is convergent in V, and sigma of the norms of the Vn's is divergent in R. Then in this case we say sigma of Vn is conditionally convergent. Conditionally convergent. So this should remind us of what happened on the real line. As I told you, many of the properties will inspire ourselves from the real line, because the real line is a special case of what? Of a normed vector space, or a Banach space. Next, I would like to talk about a concept that is extremely powerful, and it fits perfectly using the series, and we will know more throughout the web notes when I talk about, for example, operators defined on and the properties of operators, when we have some big theorems, fundamental theorems in Banach spaces. Then in this case we will get more properties. But let me introduce this concept here, and then I will go over it over and over again throughout the web notes later on. Okay? So here I want to talk about the concept of Schauder bases. Okay, so first let me take an example which will also be a motivation to us for this concept. Okay, so we have seen as an example of a Banach space the case of little LP. So what's little LP? These are sequences, real sequences, such that sigma of xn to the power p is finite. Okay? And of course we have a norm for xn that we call p. Norm p is sigma of xn to the power p to the power 1 over p, and we are taking p greater or equal than 1. And this is the sum from 1 to infinity. Okay, so LP with this norm is a Banach space. Okay, now let us introduce what's known as the canonical basis. So we take En equal the sequence 0, 0, 0, 1, 0, 0, etc., where the 1 is on the nth term. So E1 is equal to 1, 0, 0, etc. E2 is equal to 0, 1, 0, etc., etc. Okay? So we get this sequence of vectors ENs, and now we take a vector v. Let v belongs to LP. Okay, so we know that v is equal to a certain sequence xn, and take now v minus sigma of xi ei from 1 to n, and let me call this Rn. In other words, the remainder. So again, this will be what? Xn minus sequence x1, x2, xn, 0, 0, etc. So this vector Rn is equal to 0, 0, the first n coordinate, and then we have xn plus 1, xn plus 2, etc. Okay? So the norm of Rn P is going to be sigma of xk, k from n plus 1 to infinity to the power p to the power 1 over p. Okay? So since the series sigma of xn p is convergent, okay, we conclude that the norm of Rn p goes to 0. Okay? So the limit of the Vn's, the limit, let's go back to Rn, this is the definition. Okay? So it's V minus, so the limit of sigma of xi ei, I from 1 to n, when n goes to infinity, is exactly V. Okay? So you see here, in fact, V can be seen now using the language we just developed on series, okay? That this is the total sum of xn en from 1 to infinity. And this is amazing. Okay? So every element in LP can be seen as a sum of a series, okay? Let us show that the sequence xn is in fact unique. Okay? Assume that V is equal to sigma of xn en equal sigma of yn en. Okay? And what we're going to show now is that xn equal yn for every n. Okay? So it means that the sequence sigma of xk ek from 1 to n and the sequence yk ek have the same limit v. So their difference will have a limit 0. So limit of the norm of the difference xk ek minus sigma of yk ek is equal to 0. Okay? Okay, so now note that the norm of sigma of xk ek sigma yk ek is equal to, and this of course from k equal 1 to n, okay, xk minus yk to the power p to the power 1 over p from 1 to n. So in particular, fix k. Not k because we're already using k. Let's use another symbol, fix n0 greater than 1. Okay? And let n greater than n0. So we know that absolute value of xn0 minus yn0 is less than the norm of sigma of xk ek minus sigma of yk ek from 1 to n from 1 to n. Okay? Because of the definition here that we have right here of that. So one of them here is going to be this one right here. So if we let n go to infinity, and using the property that the limit of these norms here, these norms goes to 0, we get xn0 equal yn0 for any n0 greater than 1. So, which means that the xn's here, the xn's in this, we get the xn's are the same as theyn's. So this tells us some kind of linear independence of the en's, but I have to clarify this a little bit later. These are series we're talking about. We're not talking about finite sums, okay? This is infinite sums, okay? Great. So the conclusion is, so what's the conclusion of all this? Conclusion, okay, for any v in LP, there exists a unique sequence of xn's such that v is equal to sigma of xn's en's from 1 to infinity. Okay? Of course, the xn's will be called what? The xn's will be called the coordinate of v, okay, coordinate v with respect to the sequence en. Because if we change en, if we take a different sequence, we may have, as you can imagine, different coordinates, okay, as we did in the finite dimensional case, okay? This conclusion suggests the following, okay? So generalization of this. Let V be a Banach space. Okay. Let En be a sequence of vectors in V, and assume that for any V in V, there exists a unique sequence xn in R such that V is equal to the sigma of xn en from 1 to infinity. Okay? Such sequence en is called a Schauder basis of V. So the case of little LP, we just saw that little LP has a Schauder basis, and we have an explicit Schauder basis. Okay, there are many Schauder bases. I mean, as we did for the algebraic basis in vector spaces, here also we don't have uniqueness of the Schauder basis. And the one that we learned on LP, in the case of LP, there are what we call the canonical Schauder basis, but there are other bases that one can come up with. Okay. So note that the proof I just did of uniqueness of the xn's, clearly that the en's are linearly independent in V. Okay. In particular, the norms of the en's are not equal to 0. Okay. So if the norm of the en's are all equal to 1, then we call en a normalized Schauder basis of V. That's the case of the en's we just found before. In the case of little LP, they have all norm 1, and therefore it is a normalized Schauder basis. Let me make a remark here about Schauder basis, okay? Because this is very common that the students confuse Schauder basis with the basis, the algebraic basis in a vector space. So remark here, okay? Just to clarify this point, to see that they are fundamentally different. I mean, other than they share that they are linearly independent, and they do span, in fact, but we have to be careful. We have to be very, very careful. So here first, okay? Let V be a vector space, a normed vector space, or Banach space. Makes no difference. Let En be any sequence of vectors in V. Okay? So when we write V, so when we write V belongs to the span of the en's, what do we mean? We have, this means that there exists alpha 1, alpha 2, alpha k in R such that V is equal to alpha 1 E1, alpha 2 E2, alpha k ek. So what we need to be careful about is that it's a finite sum. So the span is a finite sum. Okay, it's a finite linear combination. So now, when we take a sequence Vn in V, so now, if we take Vn sequence in V, okay, so for each n, oh, I'm sorry, such that, sorry, I'm assuming that this Vn's belongs to the span, such that Vn belongs to the span of the en's, of the Vk en's for all k. Okay, so if I assume that all the vectors are in the span, then we have Vk, which is a linear combination of the ei's, or the en's. So we get alpha 1k E1 plus alpha 2k E2 alpha k n En for some n. that depends on k. Okay? For every k is a finite linear combination of the vectors ENs. What's interesting is when you go from vk to vk plus 1, then this is also equal to certain etc. And the last one will be k plus 1, n k plus 1, e n k plus 1. So you see this here and this one here have nothing in common. Okay, so they differ. Okay, so this is in general a sequence in the span. Okay, in the case of a Schauder basis, when the ENs is a Schauder basis in V, then when we write V equal sigma of xn en from 1 to infinity, we have the sequence of the partial sums from xk ek from 1 to n, and they stay the same. We keep adding. So when you go, so this is again Vn is equal to x1 e1, x2 e2, xn en, and Vn plus 1 will be x1 e1 plus x2 e2 plus xn en plus xn plus 1 en plus 1. So you see we're adding this block. So this block is the same. This is, of course, these vectors, they all belong to the span of the ENs. Okay, because this is a finite linear combination, and the VNs converge to V, so V belongs to the span closure of the ENs. Okay, and that is your V. This is in the case of a Schauder basis. If it's not a Schauder basis, okay, so if V belongs to the span closure, then we do have the VNs, the VKs, which converge as you see them here, but you cannot say that they are coming as a partial sums of a series. So that is different. In other words, the coordinate here is very important. These coordinates are dependent on the vectors. They are changing. In the case of Schauder basis, we can have them in a way that they don't change, and we get, of course, the partial sums of a convergent series. Okay? So this is very, very important to make a difference between Schauder basis and linear basis, or what I call algebraic basis. Okay? One more remark here as well. We can talk about a remark here. One more. So what if you have V, which is a Banach space, be a Banach space? Okay, and let En such that, okay, En is a Schauder basis, but not for the entire space, only for the span closure, span W, which is the span closure of the ENs. Okay, so in this case we talk about, to make a difference, whether you have a Schauder basis that spans the entire space or only a smaller space. So in this case we talk about a basic sequence. So we say En is a basic sequence. Okay, so it only spans a smaller subspace, not the entire space. Okay. Anyway, the last part, or the last question that one may wonder is if any Banach space, so this is just a simple question. Okay, we saw it for little LP, and the question is, does problem, okay, does any Banach space have Schauder bases? Okay, and before we answer this question, let us make a beautiful result, theorem. Okay, let V be a Banach space. Okay, assume En is a Schauder basis of V. So V has Schauder basis. Then V is separable. Okay? So in other words, we have a dense countable subset in V. Okay? Indeed, proof. Consider Dn to be the set of all vectors sigma of Q I E I from 1 to n, such that the Qi's are all in Q, the set of rational numbers. Okay, so Dn is basically, okay, there is a one-to-one map bijection equivalent to Q to the power n, which is countable, for all n greater than 1. Okay, so the n's are all countable, and set D to be the union of all dn's. So we know that D is a countable union of countable sets, so is countable. Okay, let us prove that D is dense in V. Okay, let V vector V and epsilon positive. We want to prove that the open ball centered in V with radius epsilon intersect D is not empty. This is what we need to prove. Okay, great. Great. We know that the ENs is a Schauder basis of the entire space V, so there exist xn's in R unique such that V is the total sum of xn En from 1 to infinity. Okay. So for that epsilon, there exists n0 such that for every n greater than n0, V minus sigma of xn En, xk from 1 to n, norm less than epsilon over 2. Because at the end we're going to find 2 epsilon, and what we need is epsilon in the ball, so that's why I'm dividing by epsilon over 2. So in particular, we have the norm of V minus sigma of xk ek less than epsilon over 2 from 1 to n0. Okay? Now, for every k, now let us look at the density of Q in R. For every k greater than 1, there exists qk in Q such that the absolute value of xk minus qk is less than epsilon over 2 to the power k, the norm of ek. Keep in mind that the ek's are not equal to 0 because Schauder bases, they're linearly independent, and therefore their norm is not equal to 0. And that's why I'm dividing by the norm. If they were normalized, then we don't need to put them there. They will have a norm equal to 1. So now we have okay, the following. The norm of V minus sigma of qk ek, k from 1 to n0, is less or equal, from the triangle inequality, the norm V minus xk ek from 1 to n0 plus, okay, the norm sigma of xk ek sigma qk ek from 1 to n0 from 1 to n0, okay, which implies that this one here is less than epsilon over 2, and the other one is in fact the norm of sigma of xk minus qk ek from 1 to n0, and we use the triangle inequality, less than epsilon over 2 plus sigma absolute value xk minus qk, the norm of ek from 1 to n0. And again, using the definition of the qk and xk, this will be epsilon over 2 plus sigma of epsilon over 2 to the power k from 1 to n0, which is less than epsilon over 2 plus epsilon over 2, because the sigma of 1 over 2 to the power k from 1 to infinity is 1/2, okay, which gives me epsilon. Okay, so the ball centered in V with epsilon radius intersect D n0 is not empty, and if it means D n0, it means D. Okay, therefore, if you have a Schauder basis, the Banach space is separable. So, question becomes now: does any Banach space, or is any Banach space separable? The answer is no. Okay, we have theorem. So first, recall little L infinity. So it's the space of bounded sequences, and the norm of any element in little L infinity, call it the norm infinity, is the sup of absolute value of xn. Okay, so theorem, beautiful theorem, the space L infinity is not separable. Okay, and since it is not separable, therefore it does not have a Schauder basis, and that is an exam that we are looking for. So proof of this, because we did not do it before, it's good to see it at least once. Let A be a subset of n, A non-empty. Okay, and define the vector V sub A to be the sequence xn with xn equal 1 if n belongs to A, and 0 if n does not belongs to A for any n. Okay, so this way we have these vectors in little infinity because the values are 1 or 0, so it's bounded. Therefore, the sequence xn belongs to little infinity, number 1. And if you take now, if A and B are subsets, non-empty subsets of n, we get VA equal VB if and only if A is equal to B. Okay? So And if A is different from B, then not only VA is different from VB, but the norm of VA minus VB is 1. The distance between each one of them is 1. So now, how many do we have? So if you look at the set of the VAs, A subset of N, A non-empty, okay, this is in one-to-one correspondence with the subset or the power set of N where we took one element out, and this is uncountable, is not countable. This is one of these exercises that you learned in real analysis, okay? So this set is not countable. The power set of N is not countable. N has aleph 0 cardinality, and the power set has aleph 1 cardinality. It's the same cardinality as the reals, the set of the reals are, okay? Good. So this set is not countable, okay? And the distance between them, they are one separated vectors. In other words, the distance between every two different vectors is 1. Okay, it's very important. So now, assume L infinity is separable. Okay, let D be a countable subset of L infinity, which is dense. Okay, so it's dense in infinity, and you have a countable set. Okay, good. It's very easy to see that for any epsilon positive, we know that for any v in the space in infinity, the open ball, this is intersect, with radius epsilon, intersect D is not empty. Okay, using this, the definition of density, using this, we see that L infinity, in fact, is included in the union of the open balls centered at vectors in D. Okay, so how many balls do we have here? We have countably many. Okay, countably many balls, and you have this L infinity there. Okay, I'm sorry, these are balls with radius epsilon. Okay, so here take epsilon equal 1/3. Okay, so L infinity is in the union of all the open balls centered in capital D with radius 1/3. Okay, and they are countably many. But then the set for every A, VA belongs to one of these balls. So for every A, okay, in subset of N, A non-empty, VA belongs to the union of these balls. Okay? So one of these balls, because we have uncountably many, not countable VAs, one of these balls will contain plenty of VAs. So here, one of the balls that exists D in D such that the open ball D 1/3 contains more than one VA. Okay, in fact, contains uncountably many. So it can't be finite. It can be infinite, in fact. Okay, but anyway, I need just two. Okay, so let's say VA, VB belongs both to this ball. Okay, so the norm of VA minus VB is less than the norm of VA minus D from the triangle inequality. D minus, oh, I'm sorry, this is infinity, norm infinity. D minus VB. And since they belong to that ball, so this is less than 1/3 plus 1/3 equals 2/3. But we just saw before that the norm of VA minus VB is equal to 1. So 1 is going to be less than 2/3. And this is the sought contradiction. Okay? Therefore, little n infinity is not separable Therefore, little infinity cannot have a Schauder basis. This is an example of a space that does not have a Schauder basis. Thank you very much for your attention, and see you in another web note.